Hello everyone and welcome. My name is Nick and today we're going to be doing some chemistry and I'm going to be looking at polar covalent bonding. Now in the last lesson I did pure covalent bonding, which is when there was a non-polar molecule. And the reason for this is because the electronegativities in the atoms were the same or very, very similar. Now we're going to be looking at atoms where there's a little bit more of a difference in electronegativity, and therefore you have a positive and a negative side. And that's why we call it polar covalent. So let's look at water. Now, water is H2O. We all know that. And so if we look at the electronegativity of hydrogen, it is 2.1. And hydrogen has one electron, one valence electron. If you're not sure about the valence electrons, check out the first video I did on the periodic table where I talk about valence electrons, which are electrons in the outer orbital. Now, oxygen, each hydrogen brings one valence electron to the party, and oxygen brings a total of 1, 2, 3, 4, 5, 6. So one there and one there will bond with each hydrogen, and these extra two pairs are what bends that molecule. So when you're doing the molecular structure of water, if you get into doing that, you'll see that your water molecule gets bent and it's leaving an angle of 104 degrees. So 104.5, I think it is. So you've got this bent water molecule. That's not important though. What's important is that it is polar. Now let's look at oxygen. Its electronegativity is 3.5. And so our difference in electronegativity, let's do the H for this one because then we're going to get a positive. So the difference in electronegativity, 3.5 minus 2.1 is going to be 1.4. And when we look at our table, the electronegativity difference between 0.4 and about 1.7 tells us it's polar covalent. So we just need to look at the difference in electronegativities if you're given them, and it's the quickest way to figure out whether it's polar covalent, pure covalent, or ionic, which is what we'll be doing in the next lesson. But there is another way of doing it, and that is by drawing the molecule. So if we look at H, H has got a slightly positive. If we look at our +1, +2, in the first periodic table video, I looked at this. I'm going to put a link to that video now so you can go back there and have a look why this is +1 and +2. And then this is -1 and -2. And so we see our hydrogen is slightly positive. I'm going to put this in as -2 in red, -1 rather. And so this is a positive. So we donate this symbol plus, and so this is slightly positive. And then we have this is our negative pole. Okay, so what does that mean? Why do we call it polar? Well, if you think of a magnet which has poles, the Earth is one big magnet with a north and a south pole. So let's look at our magnet. And it has a plus end, which is positive, and it has a negative end. These we call poles of the magnet. Well, these molecules are exactly the same. You have a positive pole and a negative pole. So we see how our electronegativity difference in the atoms helps us to figure out if a molecule is polar or non-polar. Now, you don't always get given the electronegativities, but you can draw them to figure out whether a molecule is polar or non-polar. And let's look at the example that I did before which was the NH3 and BH3, and compare them. So let's first look at the BH3, which was non-polar. So first of all, the BH3. Now the hydrogen, I'm going to draw another one because I'm going to be doing NH3 as well. Hydrogen each contributes one valence electron. Now the boron brings 1, 2, 3. And so when we look at it, there's no extra molecule, the extra electron pairs like in the water. So we've got this balanced non-polar molecule here. And if we look at the difference in electronegativities as well, we see that hydrogen 2.1, boron 2.5, 2. Boron is 2, I'm going to write that there. I can write it here. 2. Then our change in E is 2.1 minus 2, which is 0.1, and it falls into the pure covalent category. We also see that all of the electrons are used in bonding. And so there's no overall charge. And we have this non-polar molecule. Now let's compare that to NH3. Now N, if we go along, has 2 extra valence electrons. So N has 1, 2, 3. And then an extra 2, which are there. And we know the hydrogen is 1, 2, 3. Now, this central atom obeys the octet rule, and hydrogen always requires just 2 electrons because it's in the first orbital. Just a note on boron, why it's not obeying the octet rule, the BH3 molecule, because there's not enough electrons. There's only 1, 2, 3, 4, 5, 6 electrons anyway. So it's just going to look like this, and it doesn't obey the octet rule. But usually when we draw these molecules, the middle atom and the outer atoms, if they're not hydrogen, need to obey the octet rule, meaning they need 8 electrons. But I'll go into more detail into the octet rule in another video if you want to. So if you do want me to go into the octet rule, just write a comment in the comment section. And if I don't see any comments, I don't have to do the video. Right, so NH3 is 3, and hydrogen is 2.1. And so when we subtract them to get our change in E, which is our change in electronegativity, or difference in electronegativity, we see 0.9 falls into the pure covalent category. So the H is then a slightly positive, and so that's where you will see this symbol, and the N is a slightly, what is your negative pole, and so you have your positive and your negative poles. And let me just do that in light blue and red so that we are consistent in showing how it's a little bit like a magnet in that it has a positive and a negative side. So that is our polar covalent bonding. Next up, we're going to be doing ionic bonding, which is when the electronegativity between atoms is even bigger. So hopefully that helped you. And if it did, please find the subscribe button somewhere down below and click it, and share with your friends, and like the video and all that good stuff. And I will see you in the next lesson.